Sorry, I did not unmute. So welcome again to the ones online. Okay, so last week, sorry, that was my typical way to start a lecture. No, yesterday I introduced supervised machine learning to you, and I gave you some basics of neural networks, and that was basically where we stopped yesterday, namely at a sort of general description what deep learning is. And I already told you yesterday that deep in this context means that we do not have a very simple network, but we might have a very complicated or network with several layers, with possibly many hidden neurons in such a neural network. And that is something that was impossible to train with previous technology in the 1980s, 1990s. And just about 10 years ago, people started reviving this field. And there were basically three things that allowed for a renaissance of neural networks. First, that's new technology for training neural networks. That's really essential. Then the availability of large data sets and the availability of powerful computing resources, in particular graphical processing units, GPUs. Okay. I told you that the main problem of standard neural networks were the vanishing gradient problem. I will not go into detail what that is, but it means more or less that you cannot train multiple layers in a meaningful way. Okay, that the error signals that I told you about that back in the network are quickly getting smaller, and they are essential for updating the weights in the network. And if they're exponentially decaying, that's actually what happens with 1980s technology, then already in the second or third layer, they're so small that virtually no updates to the weights can be made. And that's why it's virtually impossible to adjust the weights of a deeper network because of this vanishing gradient problem. And there were some first approaches about 10 years ago where something called pre-training was applied, where multiple layers were stacked onto each other in an unsupervised fashion. That's a relatively complicated procedure and requires a lot of experience as well. But nowadays, it's more common just to have regular multi-layered perceptrons, so multi-layered feed-forward networks with possibly many layers, possibly many hidden neurons, and to train them in a regular supervised fashion with backpropagation or with a similar algorithm as backpropagation, because some new activation functions and training methods were available. Okay, the most important thing about deep learning is that if you do it right, which is a fishy thing and requires a lot of experience, you have the possibility to have multiple layers of abstraction in the network. So what does that mean? For instance, if we work on image data, then the first hidden layer learns very basic image features like 3x3 filter masks or things like that. So maybe little edges, little corners are detected. And then in the next layer, they're put together patterns. And in the next layer, maybe you will have something like pieces of an eye, pieces of an ear. And in 2-3 more layers, things are put together into faces. And then you might have a layer where you have multiple neurons, all of which put together all of which correspond to some to some special patterns like human faces, dog faces, cat faces, and things like that. Okay, so we really have multiple layers. I will show you an example. Okay, one of the key things to modern deep networks is that they facilitate so-called sparse representation, so that you have some clearly defined paths in the network that encode for specific patterns in a sort of robust fashion. And there are basically two things that are important for that. One of the keys to supervised deep learning are the so-called ReLUs, the rectified linear units. This is a very possibly strange activation function compared to the classical threshold in perceptrons and the sigmoid in traditional feed-forward neural networks. It's the identity below zero, and it's zero below in the negative area, and it's the identity in the positive area. So this weighted sum that we take as the net input of one neuron is transformed by this strange function, which means every negative value is annihilated, remains zero, and for everything else, it's just the identity. And this is an activation function that avoids the vanishing gradient, because the error signal is not multiplied by a constant that is smaller than 1. The gradients are either 1 or 0, and if they're 1, the error signal flows freely without vanishing, without decaying. Okay, and that's one of the keys to solving the vanishing gradient problem on the one hand, and on the other hand, since every negative value is squashed to 0, it facilitates a sparse representation. And moreover, there's another technique that is very common. It's called dropout. It works in the way that during training, you randomly set a certain fraction of neurons or the activations of them to 0, which means you force the network always to think a little bit in alternatives, right? So it more or less corresponds to impeding the network. So you actually force it to think in different paths, to think in different ways, and that serves for regularizing the network, for making the network more robust. Well, it's not really a good analog, but if you think about random forests that I told you about yesterday, where you have this random selection of features at each split when you create the tree, it's a roughly similar thing. This is called regularization, where you try to force the network not to overfit too easily. In this case, by putting some activation to zeros and thereby forcing the network to also use different paths. It can only be roughly compared to the random feature selection in random forest, but it's a similar principle in some weak way. Okay, so those are two of the most important things that were developed. Both are relatively simple, actually. That facilitate of deep neural networks that regularize well, that don't have the vanishing gradient, that learn well, and so on. Okay. In the meantime, several updates of these activation functions have been published, like leaky ReLUs and also ELUs. That's an activation function developed by colleagues from my institute. I'm not going into all of the details, but you should probably know at least these two basic things, because they are keys to making deep learning work. Okay. I was already motivating deep learning with examples from image processing. Okay, so And maybe you have heard or seen fantastic stories about deep learning in image analysis, right? They do not really work in the way that every pixel is one input to the network. That would not work. So imagine you have a high resolution image, something like, I don't know, VGA resolution. That's not so high res, but still you would have about 1 million pixels, okay? If you have 1 million pixels, if you take literally every pixel as one input, layer consisting of 1 million neurons, right? Next layer, you have, I don't know, several hundreds or thousands of neurons. You would have to have 1 million times this number of hidden neurons weights between them, right? And that would mean you have a vast number of parameters to fit to the data. And the more parameters you would have billions of parameters. And if you have only a few thousand images, or maybe tens of thousands of images, you cannot fit billions of parameters to such a number of samples. And on the other hand, suppose you want to detect a particular object in an image, for instance, a face, okay? If you take every pixel independently, you would have to see the face in every possible location in the image, because you cannot adjust a weight in the bottom right corner, or you cannot adjust weights in the bottom right corner to detecting images if an image never appears there. That's totally unpractical. That does not work. And there is a relatively simple but extremely clever idea to circumvent this problem, and especially to circumvent not only the problem of the localization, if the objects can freely move on the image, but also to solve the problem of this vast number of parameters. And that is what is called convolutional neural networks, or CNNs. Okay, it's not a news station in this case. It's a common abbreviation in neural networks, CNNs. So how do they work? They work in the way that you do not, in each layer, have a full connection between all pixels and all hidden layers. You just work on little patches of the image, and you have basically the same network for every little patch that you move over the image, okay? So, for instance, if your first layer consists of a 3x3 filter mask only, okay, to detect little edges or corners or something like that, or to detect little details of an eye or whatever, okay, then you just have 3x3 patches, and you move the same network over the entire image and use the same weights, okay? So that the learning of these 3x3 filter masks is disentangled from the actual position, and you use the same filters everywhere in the image, okay? Well, 3x3 filter masks cannot fulfill such complicated things like face detection or distinguishing different races of dogs. But you have to, of course, you also have to stack them. So you have multiple levels of those convolutions stacked onto each other, hoping that they would learn increasingly complicated things in the end, okay? So let me show you a little example, okay? So suppose here we have a very, very small input image, only 10 by 10, right? And suppose we want to learn one 3x3 filter, okay? That means we take a little patch, okay? A 3x3 patch of the image, and we compute one value of it, okay? So basically you have 9 weights plus a constant offset, okay? So basically you have 10 parameters that correspond to this little filter mask. And you can train this filter mask for every little patch. Okay? Not only this one, but then you move it one to the right, another one to the right, and then you start in the next row. Okay? Altogether, if you compute these results for all possible patches, you will end up in an 8 by 8. Okay? So you have 10 parameters, and on only one image, you actually have 64 subsamples, so to speak, to fit your parameters on. Okay? So every image is a multitude of different patches that you can use to train or to fit the parameters of this little filter to. Okay? Is that clear? Of course, you do not only have one single feature map. Of course, you have multiple such feature maps. Okay? You need multiple filters. You need an edge to the left, an edge to the right, a top left corner, top right corner, bottom left corner, and so on. And maybe if it involves colors, you also have 3 input layers for red, green, blue, or hue, saturation, value, or something like that. So it can become much, much more complicated. And maybe you have not those 5 feature maps that I symbolically put together here, but maybe you have even thousands of them, okay? Which corresponds to 1,000 hidden neurons in the first layer. But each of those filters has relatively few parameters, and you have extremely many samples, patches, to fit, to optimize the parameters of them, okay? So suppose we have then such a feature map. It may consist of few or also of very many such filters. Repeat this, okay? And stack another feature map onto the feature map that you just created. If you do a 3 by 3 filter mask again, then you will have a 6 by 6 layer, okay? If you have a 5 by 5 filter mask, then it's maybe only 7 by 7 in the first. Or if you do not advance the windows by only 1 pixel, but by 2 pixels, it becomes less. So if you stack them onto each other, the network's resolution gets smaller. And also the so-called receptive field of each of the neurons is something that spreads across the image. You can also have a downsampling to force more compact representations. And depending on what you do in the end, you might continue in that direction and also decompose things again, or you might have a fully connected regular layer that just puts the things together in the end. You may have up to hundreds of such layers in image analysis, okay? Let me talk a little bit about the ImageNet challenge. The ImageNet challenge is an image recognition challenge that has been organized at a very prestigious computer vision conference for several years. So for years, people were trying to be good in that challenge. And that challenge consists of a lot of images and a lot of classes. And you had to classify these images and assign them to classes as good as possible. Okay? And just a few years ago, after the accuracy of that in that challenge has sort of saturated, one guy came up with a convolutional neural network, and it was even a guy who was relatively ignorant to classical computer vision, and I think there was a several % leap in the accuracy. So typically, an image processing expert would start with handcrafting such filters and using the knowledge in image processing to facilitate good detection or good classification rates. If you have such a deep neural network, then maybe the network will learn the filters, the feature maps by itself, such that they fit as well as possible to the image recognition task. Okay? And now for years, the convolutional neural networks have won this ImageNet challenge every year. And this ImageNet challenge not only consists of millions of images, you also have thousands of classes. And you have images in which you have to detect basketballs or ping pong balls. You do not have only classes for dogs or a class for dogs for dog detection. No, you even have different classes for different races of dogs. So you have to put the whole image in context with everything. You have to identify the size, the shape, and the fur color and the fur texture of a dog in order to properly assign it to the right dog race. Okay, so these are really, really difficult tasks, and they're solved nowadays without the slightest prior knowledge about image processing and without the slightest prior knowledge about the classes that you have to find in these images, right? It's just a matter of having enough samples, of having enough computing power, and of having the smartest new technology for setting up the architecture of such a network and for training such a beast of such a huge neural network. Okay, so maybe I don't have it on my slides, but maybe you can quickly Google Google's Inception network. You will find the architecture. It's amazingly complicated, but it has won the ImageNet challenge. I'm not sure. I think it was 2 years ago, maybe in 2015. I'm not absolutely sure. But I think in 2016 it was already another network by Microsoft. So all of these IT giant companies, they're competing with each other. They all have hundreds of people in deep learning and trying to compete with each other. So just in case you're already an expert in deep neural networks, you will definitely not have any problem to find a job. So even in the academic area, it's sometimes hard to get good people because the IT giants are hiring all the people and they paying ridiculous salaries even. So this is at the moment, this is really the time of people who know these things. Okay. I already mentioned more or less how CNN training works. So you have the same weights and this for each patch, and you actually update every weight as if the patches were different samples. And you have fully connected layers on top that are trained as usual. Okay, there's a typo, sorry. It's not May pooling, it's max pooling. Okay. Okay. So here is an example. It's relatively old. What you see here is some images that try to visualize what each neuron of a convolutional network learns. So here in the first layer, you have relatively simple textures and patterns. So what you see here, this strange looking image is actually one that shows with which image you can maximize the activation. That gives a good hint to what the neuron is actually most sensitive for. And next to it, you see the true image from the training set that gives the highest activation, okay? So you see here, for instance, you see some patterns here that obviously corresponds to edges, and this one here corresponds to homogeneous green areas, and so on. And this is the first layer. So you see that these are relatively simple patterns that are learned. In the second layer, you already see that these simple patterns from the first layer are combined into more sophisticated, more abstract patterns, right? So like these textures here, right? These stripes. So you have whereas you have only vertical edges in the first layer, you can now put them together into striped patterns. Here, the second from the left in the top row, and I have to say that for the people online because they don't see what I'm pointing at. This one you see relatively thin stripes, and on the top in the top right corner you see also vertical stripes, but broader ones, wider ones. Okay, and here you see in the bottom right corner you see edges that may be parts of windows, for instance, right? And in the next layer, maybe these patterns are put together into more complicated patterns, and suddenly in a few more layers you have the more complicated patterns put together into buildings and faces and animals and whatever. Okay, so if you do it really right, then this is exactly what should happen, that you have multiple layers of abstraction in your network, and the more you advance in terms of the layer, the more complicated the patterns are, such that in the end, the final classification, there is a dog of a German Shepherd or a pit bull or something like that, becomes relatively easy. Okay, you cannot infer things like that from the simple patterns of the first layer, but if you put them together into more complicated patterns and textures, then if you have the right architecture and the right number of layers, then the final classification task in the very last layer will be relatively easy. And these architectures, these convolutional neural networks, the basic idea goes back to Yann LeCun, has been extremely successful in image processing, and computer vision image processing now is full of convolutional neural networks. They have become one of the most promising new technologies in this area and really have boosted the performance. This is an example from my own group, from our institute. I'm not personally involved in this research. I'm still mainly focusing on bioinformatics, but because of our competence in deep learning, we have been selected by Audi as the primary deep learning partner for their research on self-driving cars, on autonomous driving. And one of the most important steps in visual perception around the vehicle is so-called semantic segmentation. And semantic segmentation is about splitting up the image into areas of different types, which means actually you segment the image, but not according to colors and textures like in classical computer vision. No, in terms of objects, and you have multiple possible objects, you have multiple classes. You see all these classes here: bicycle, motorcycle, train, bus, truck, and also road, sidewalk, pole, fence, traffic sign, and so on, right? And here is a semantic segmentation of a scenery that's, I think, a drive through Stuttgart. It's not made by Audi, it's a consortium involving Mercedes, but these data are public. Yeah, you see even the Mercedes star here. So we use this data to optimize our methods as well. And you see, well, it's not entirely perfect, but it's important that largely the image is properly classified correctly. And actually, this is not the latest result. We have been improving these results dramatically in the last months. And there's also one colleague from Malaga, who you may know, Jose Ajona, who now works with us in this project. Okay, and this is not something that you do in the lab, and that just has to work once. This is something that is expected to run online, more or less in real time, on embedded hardware in the car. Okay, we're not yet there, but with the projected hardware, we're already able to analyze 5 to 10 frames of images in that resolution properly. Okay, we hope that, of course, hardware will advance in the coming years, but we're not far away from the actual goal. This is, of course, not a network where you have a fully connected layer on top, because this is a classification that does not classify the image as a whole, but it classifies pixel per pixel. So this is a so-called fully convolutional network where the input has the same resolution as the output. So we have to output a class per pixel. And this requires special decoder, encoder networks with connections in between to have a good and sensible resolution of the result. Okay, a completely different subject, but also a success story of our institute is the TOX21 challenge. This is about drugs or chemoinformatics at large. So, well, you probably know that there are toxic substances in the world, right? And you know that there are drugs, or in other words, any chemical substance that you eat or inject or inhale or whatever has the potential to move in your body, to move into cells, and there in these cells to bind to agents in the cells like proteins or other compounds, thereby altering cellular processes. Okay? So if you take a drug, I'm not talking about legal drugs, I'm talking about regular medicine, right? That the thing about such a drug is that it spreads through the blood system in your body, goes into all the cells, right? And binds to a certain protein, for instance, for inhibiting an inflammatory reaction, okay? And if this drug targets the right protein, it has a good and desired effect. The drugs are seldom so specific that they only target this single desired protein. They may also target other proteins or other agents, maybe somewhere else in the body, and that's what is called a side effect. So that's something you don't want. And when you optimize a drug, when you develop a drug, if you're working for a pharma company, you try to maximize the desired effect and you try to minimize the side effects, okay? And this is a lot of testing that you have to make. This costs enormous amounts of money. You have models, maybe cellular cultures, special biological assays to measure biological effects, no matter whether they're wanted or unwanted. And in recent years, there has been a strong trend towards computational approaches, where you just want to see the structural formula, the structure of the compound, and you want to predict which biological effects it has, okay? From the structural formula of the compound. Of course, that would reduce the costs and the efforts for biological testing dramatically, and also in later stages even reduces animal testing and clinical studies and so on. Okay, but at the moment we're talking about early stages of drug design where typically biological assays, cell cultures, and things like that are used. Okay, so to be able to predict biological effects would be a great advantage. So there are multiple approaches for that, but one common approach is machine learning, an approach that has become common. And it works in the following way that, of course, you have huge databases of compounds, along with huge databases of which biological effects have been measured for that compounds. So you have a classical machine learning problem. You know that this compound has this effect this compound does not have this effect. So you have compounds that are active for specific proteins and ones that are not active. And then you want to identify which patterns in the structure are responsible. Can you predict for a new compound whether it will be biologically active on this particular protein or not? Okay. So we have been cooperating with pharma companies, in particular with Janssen Pharmaceuticals in Belgium for years, and we have gotten a lot of experience. We started with special graph kernels on compounds and support vector machines some years ago, and in the meantime we have more moved into using deep learning for that. Now, that's just an introduction. Now let's talk about the TOX21 challenge. The TOX21 challenge is a huge multi-million-dollar effort challenge that has been set up by the NIH mainly, but also by EPA and FDA. And it's not about drugs, it's about toxicity. I mean, toxicity or different types of toxicity are also biological effects. Of course, highly unwanted, right? But here the goal was to predict different types of toxicity, whether a certain compound is liver toxic or different types of neurotoxic, or I think maybe kinase inhibitor, blah blah blah, things like that. I don't know the details so well. It's not important at that point. It's just important to know that there are 12,000 compounds for which 12 different toxic effects have been tested. Okay, so that means you had to do 12,000 times 12 biological experiments, and they even built robots for doing that, because that would require lab work for years to do that. And the goal finally was to predict toxicity. Okay, to have a computational model that predicts toxicity. We used very many features of these chemical compounds. We used the ECFP4 fingerprints that actually corresponds to the presence or absence of little substructures in the compounds, along with chemical descriptors like hydrophobicity and whatever. There are many of them. Okay, and additionally, toxicophore features, so substructures that have been previously reported to be toxic, and so on, and scaffolds and blah blah blah. So a lot of features. This was a fully connected network. You cannot really have convolutions on chemical structures. That does not really work. So this is a huge network. You can imagine if you have tens of thousands of features and with multiple layers. And finally, we won the challenge. Okay, so there are two panels: nuclear receptor panel and stress response panels. So each of those panels had 6 single prediction tasks. I don't know exactly now, it's online, how many of the single prediction tasks we won. I think 6 of the 12. But altogether, we won both panels and the grand challenge, which is overall of all 12. And the hierarchical representation of the deep network, because of these multiple layers of abstraction, allows to find out which substructures are encoded in particular neurons in the hidden layers, and thereby we found some specific so-called toxicophores, so little substructures that are essential to toxicity. And some of them were known from textbooks, from literature, and some of them were completely unknown to the chemists. And there were really some surprises that some said, okay, I never looked at that, I never saw it, I never found it in literature, but if I look at it, it really looks plausible that it might fit into the pocket of this particular protein and cause some damage. Okay? So that demonstrates also that deep learning can be applied in totally different contexts. And this is so you see here, this is a typical convolutional example for image processing, and this is even a standard, old style, if you will, fully connected network. Okay, so what is this deep learning thing about? So for years now, it has been constantly in the media. The foundations have been laid some long time ago, including my boss, Sepp Hochreiter, who published some seminal works that have been neglected for years and just recently got more attention. It's really great in research, but it's also great in IT companies. And it has been called the biggest data science breakthrough of the decade, and the New York Times has covered it 2 times in cover page articles. And now all the major companies that you all know have started investing in deep learning, and there were some startups like DeepMind, for instance, which was acquired by Google for about $500 million some 3 years ago. So that's really amazing what's going on. The last thing I want to talk about is one thing that I haven't mentioned yet. I've talked about images and convolutions, and I've talked about fully connected networks where every feature stands on its own without a spatial structure like in an image. But what happens if you have sequence signals, okay, like a biological sequence or a speech signal or language, right, sentences, where you cannot necessarily assume a fixed spatial structure, nor does it make sense to consider every data item, every word, or every step in a signal as a completely independent thing. So neither the convolutional networks nor the fully connected networks are the really adequate thing, especially if you don't know how long the sequences are. If the sequences or the signals have different lengths, you can never apply a fully connected network, and it's also really complicated and difficult to do that for convolutional networks. So how can we scan things? How do we do that? If we listen to language, we make sense of the language. That's just because there are many words that we forget immediately, and some context is stored in our brain, and if somebody tells us a story, in the end, we know what the story is about. And of course, we have forgotten about a lot of irrelevant words like the or in or off or something like that, where we put everything into context, okay? And especially there are some languages where you have long-term dependencies in the sentences, especially in German, right? Where a word can be split between the beginning and the end of a sentence. I don't know how this is in Spanish, and English is a little bit simpler in that respect, but there are languages where you need a lot of context. And this is something that you cannot solve with other neural networks. And the traditional approach from language processing was, of course, to analyze the grammar of a sentence. Okay. How can we do that with neural nets? Well, what we can always do is, in a similar to convolutional neural networks fashion, to move a window along the signal, along the sequence, to generate an output sequence. Okay. This does not help to, for instance, categorize a sentence with different lengths and so on. It's not really worth it. You cannot have dependencies between the windows. You cannot have any context across a sentence or something like that. So that's why a recursive neural network makes good sense. A network that actually scans the sequence, along the sequence, maybe a window or so, but has some memories, right? And you can realize memory in a recurrent neural network simply by having recurrent connections of the layers of the neurons with themselves. So you feed the output, the activation of one time step, into the same thing in the next time step as an input. Okay, that's basically the idea. The problem is that in this setting, the vanishing gradient problem becomes even worse, like in a feed-forward neural network, because what happens if you train such a thing is that you have to backpropagate the error signals not only within the layers of the network, but also because of these recurring connections through time. And if the gradient vanishes, if the error signals vanish, it means that only after a few time steps you go back from the end of the sequence, all the signals are lost. Okay, they're virtually zero, and that means that you have a dumb system that just looks at the last, for instance, in language analysis, just at the last words, but it immediately forgets everything about what is said in the beginning. Okay, so you have an extremely short-term memory and no long-term memory at all. Okay, and this is something that goes back to Sepp Hohenetter. He started with these ideas in his master thesis and elaborated them in more detail in his PhD thesis. And there was a 1997 paper published with his supervisor Schmidhuber. It's a funny title, long short-term memory. It sounds a little bit like a contradiction, but if you know what's inside, it makes good sense. It's an architecture where you have a gating mechanisms to control when input is accepted into such a memory cell and when output is released. And the memory cell inside has a so-called constant error carousel. It just updates its status by summing up. And that means that you don't have any weights involved, and you have more or less a linear activation, which means you don't have a vanishing gradient. So that's actually a trick to avoid the vanishing gradient. And the gates, the input gates and output gates, there are also forget gates and things like that. This is a very simple representation that also allows for putting things in context, and you have recurring connections, and it really works nicely. Maybe in the 1990s it was too early because the computing capacities were not there to train really large networks with such things, and also the data sets were not necessarily available. But now that we have the computing power and now that we have the data sets, we can do incredible things with LSTMs. Maybe you have heard about Google New Machine Translate, right? It's all LSTM, right? You know Siri, you know text input, so this constant context text input on iOS, you know Google speech input on Android. It's all LSTM. Wherever you go, there is LSTM, and you can even combine things. So, for instance, what happened here? This is a very sorry for the problem with the title here. You can even combine things in a very nifty way. You have a convolutional network that finds the essence of a picture, what happens in the picture, and then you use LSTM to generate the text caption for that. And this is trained really in a way that you have text captions and images together, and you train the entire network, which is a combination of a convolutional network and an LSTM network, to create text captions. Okay, and you'll see it's not only an image classification task. First of all, it creates proper grammar, and it also includes activities. So it's not just guitar, toy, dog, or something like that. You see, man in black shirt is playing guitar. Or construction worker in orange safety vest is working on road. It's not always totally red, but these are some examples for which it works really, really nicely. I mean, okay, this young girl in the pink shirt, she's not on the swing, but she's on a playground on such a scaffold. Okay, so it's really amazing. So now, as I told you, LSTM is used in many commercial and research applications in speech processing and image processing, and it's incredible what you can do. Okay, what I haven't mentioned here is generative adversarial networks that create images or that creates data as if they came from the natural world. But if you combine that, for instance, I have seen a demo where you can say a sentence or give some text and an image is created that shows what has been specified. I mean, it doesn't really work perfectly, but you can even say relatively absurd things like a school bus flying over the blue sky. Yeah? And then you see something yellow on blue background, at least. Yeah? It doesn't really look like a school bus, at least not the demo that I saw in 2015, but it's really amazing. And it's just, you need the data, you need the technology, and you need a lot of computing power, and then you can do really amazing things. Okay. Just finally, I want to mention that this is not something that you can start to implement yourself. So if you're doing k-nearest neighbor classification, you could start from a programming language like C or Java and write the whole algorithm yourself. Okay, so you have full control over everything. If you want to do deep learning, like complicated things like LSTMs combined with convolutional neural networks and so on, this would require everybody of you years of development, and you have to deal with CUDA and things like that, so GPU libraries and so on and so on. The good news is people have done that already. For instance, TensorFlow is a very general and very powerful framework developed by Google, and which is available open source and has a sort of abstraction layer that you can use it on multi-core systems in the same way as you can use it on a GPU server or even down to a mobile. Okay. So there are many things around, and each of them has its advantages and its disadvantages, but I would say probably that TensorFlow is currently the most common and the most powerful thing. It's not really easy to handle, so it's very basic. So you have to have some more abstraction layers on top of it to really work with it efficiently, because typically you don't need all the generality it offers. But there are some layers on top, like Keras, for instance. Okay. MXNet is also not totally uncommon. It follows slightly different philosophies, but for instance, on the Amazon cloud, if you buy resources on the Amazon cloud for deep learning with GPUs, then what is mainly supported is MXNet. It is available as an R package, by the way, and I will show you some code later. Okay, so some final comments about deep learning. It's absolutely exciting what's going on. Okay? And it's something that I've never seen before, because when I grew up, okay, not literally speaking, but when I've been working in research and also in applied research for years now, and it's quite typical that people are doing basic research, and there's a certain disconnect between basic research and applied research, and it takes a long time until applied research becomes really applied in commercial applications. And this is absolutely untrue for deep learning. So all the companies like Google and Facebook, some of them are even covering the whole chain from basic research. But what happens is that things are typically published immediately on arXiv, even before they are submitted or accepted to any journal or conference. And there's immediately a lively discussion about everything. And it can really happen that if you put a paper on arXiv and people find it worthwhile, that 1 month later, it is in one of the commercial products of Google. And that's an extremely fast pace, and it's really hard to keep up with it, because you need to know a lot of literature to really be up to date. And it's because there's so many people working on it, it's really amazing. And for instance, the flagship conference is this NIPS conference, this old-style neural networks and computational neuroscience conference from the 1980s, which has seen a tremendous boost in recent years. There was always between 500 and 1,000 people, and in 2014, I think it was 2,500, and in 2015 it was 3,700, and last year in Barcelona it was 6,000 people. So it's absolutely crazy what's going on. So this is something, if you want to start it, you should start it now. Okay, just definitely not the first one anymore to do anything like that. There are thousands of people, but since there is such a great potential, there are still additional people and additional groups needed to work at that. What is the downside of it? It's not something where you as a beginner. So the technologies are complicated. There's a vast amount of literature. There is much competition. Okay, and if you really want to do up-to-date things, relevant new things in deep learning, you have to know a lot of stuff. You have to have data. You need to have a lot of computing resources. At my institute, for instance, we have 35 GPUs, all of which are constantly overloaded. We have a sheet where we can, with a waiting list, who's next with running jobs on the GPU. We would love to buy additional GPUs, but they're out of stock constantly. So it's absolutely crazy what is going on. Okay, so you can have a gentle start, but it's also something that takes quite some time to get experience with, to get knowledge of all the literature and all the technology, and things like TensorFlow, for instance, they're not really easy to handle for a beginner. So it's absolutely amazing, but it's also very challenging. Okay, so that ends my general overview of deep learning. I suggest that we skip the little presentation I have about an overview of unsupervised learning. It doesn't really fit now, and I think you can also view it yourself. You have the course material. It's a crude overview of projection methods and clustering, so nothing that I think is absolutely essential at this point. Osvaldo asked me to focus more on deep learning, and that's what I did. Perfect. According to his wish. So I would now like to switch to a little bit of practice. I will also show you some deep learning, but as I told you, it's a very challenging thing. You need a lot of code, and the code doesn't run really within seconds. But I will show it to you. Okay? So do you have any questions that would make sense to ask now? Okay, so if not, I will close this. Yes?
Let's say you're starting up with machine learning, not only deep learning, right? Could you give out some pointers? Like, let's say you want to get started with it, but you don't know how to overcome problems like the overfitting of the data, like setting up some parameters to get better results. Like where to go there?
Yeah. I mean, that's a very valid question, and I don't really know where to start. So I think first of all, regardless of whether your primary focus will be deep learning, you need to know the basics of machine learning. You need to know what overfitting is, what this phenomenon is about, and that regularization, for instance, can avoid it. Actually, there are many things related to underfitting and overfitting that you cannot know in advance without seeing the data. So it always comes down to fitting hyperparameters, so to speak. in a training validation test set setting or in a multiple cross validation test setting, something like that. Of course, you should know what beforehand what makes sense. Okay, so there may be some parameters will never work. For instance, you need not, if you have a small data set, you need not test a really huge deep neural networks to analyze it because it can only overfit, right?
Yeah, but if you're using, for example, a decision tree classifier for a small data set, like how many branches should you go, like the depth of the branch?
Okay, that's a good question. I think that well, you can for in this particular example, if you want to fit a decision tree to a particular data set, then you need to adjust things like the tree depth and such things. Then the only thing you can do is to cross-validate, to fit the parameters that you actually see, which parameters give you the best test error, right? If you really want to have an unbiased estimate of the generalization performance in the very end, you cannot use this cross-validation setting anymore because then you bias hyperparameters to the entire data set. So you need double cross-validation. But advanced subject that I haven't touched so far here. In this particular example, if interpretability of the result is not your primary goal, I would advise you not to use a single tree because it will always be suboptimal. I would rather advise you to use a random forest because because of this ensemble idea and the subsampling of samples and features, it more or less, okay, that's a nonchalant way of putting it, it more or less avoids overfitting because of the large ensemble. Random forests are a good point to start with because unless you have a very unbalanced data set, you can simply drop your data into it and get a meaningful result. For support vector machines, it requires a little bit more knowledge, and for deep learning, it requires a whole lot of more knowledge. Maybe you look a little bit at the sample code I'm going to present, because you will find examples for support vector machines and for random forests as well as for deep learning. So maybe that's a good transition to start now. Okay.
For example, you can use the neural network to find timing your parameters or some evolutionary algorithm, no? Then you can play different parameters. So for the training timing, you have a fitness function. The network for the high.
I have a problem now, Oscar, because the window I wanted to share is not on the list.
Use the entire screen.
Yeah. Okay.
And then share.
Yeah.
And
okay.
then you change the.
Yes. Can you check whether you see it? Is it there?
There is some without.
Ah, okay. Okay. So, then I start. Please stop me if you see that something is not okay. Okay. So I have provided you with R code for units 1, 2, 3, 4. I will quickly browse through units 1 and 2 to show you how R code works. So, for instance, unit 1 was only this general introduction with the fish data. So I will simply show it to you how to analyze the fish data in a really simple way. So what I do here is I have to change the directory, sorry. So I read the data set. And for instance, with this, I can show a scatter plot of length versus brightness. That's obviously not extremely helpful because it's without classes. Now, with classes, then you see this is what the fish data set looks like. We have salmons more to the left and to the bottom. Okay. And we have the sea bass more to the right and up. And there is a certain twilight zone. Okay. Now let's look at these histograms. These are the histograms that I already told you. So this is the overlap that you get when you consider brightness, and this is the overlap that you get when you consider length. And it's pretty obvious that this has worse overlap than this, so this is the better feature if you take one feature only. Okay, this was already unit 1 because in unit 2 we see the more sophisticated things like support vector machines. Okay, now for unit 2, you see I'm now dealing with linear regression as an example. So here I create a little toy data set by taking normally distributed inputs, and I have a fine transformation of this normally distributed inputs plus a random noise, and this is the scatter plot, what it looks like. Now let's train a linear model. Here you see the intercept and the coefficient. Now we add the line to this scatter plot. Now let's try polynomial regression. So here you see what happens if we have a data set that is based on a nonlinear function and we fit it with a linear function, which is obviously not a very good choice. Polynomial of degree 4, and you see it looks pretty good now. Okay, and I also want to show you what overfitting can be like. This is what happens if you fit a polynomial of degree 20, and actually the data was based on a degree of 4, so it really starts fitting to the random noise in this case. Okay, now let's move back to the fish classification example, and let's try to analyze it with the one nearest neighbor. And you see, okay, I will show it a little bit larger. Is this with okay, you don't know yet. And you see, for instance, here there's a very curvy shape that is being identified as the border, and there is one blue outlier that creates a little light blue island, and there is one red outlier that creates a little light blue, a little pink island here. So this is probably not really good. So I tried to take the 5 nearest neighbor, and you see that looks much better. And if we take a 21 nearest neighbor, then see we have a relatively smooth curve here. Okay, now let's try the same with support vector machine. So I'm now training a linear support vector machine, and I'm displaying the result here. So here you see the data set. Red means positive class, black means negative class, pink means this is the area that's classified as positive, light blue means this is the area that's classified as negative. These are the support vectors, and the circles are the non-support vectors. Okay, Now, let's try a nonlinear support vector machine. Seems to be quite good, actually. Let's see how many misclassifications we have. We have 1, 2 black samples that are classified as positive, misclassified as positive, and we have 1, 2, 3, 4 red samples that are misclassified as negative. So 6 misclassifications in total, which I think is more or less the best we can get with this data set. Now, I also want to show you how to do things wrongly. I deliberately chose some parameters that, if a support vector machine that does not work that nicely. So you see, this is what happens if you overfit. You see again these 2 islands and this very curvy border. It pretty much resembles the result for the one nearest neighbor classifier, I think. By the way, this is with an RBF kernel, so a Gaussian bell-shaped kernel, which is very, very peaky with a very low variance, okay? So that you have very spiky Gaussian bells, and along with a regularization parameter that allows for very high coefficients, you can easily get such a result. And the more wider the Gaussian kernel is, and the more you constrain the coefficients in the support vector machine, and the flatter the function is, and the less complex the classification border gets. Okay. Now let's try the following. We take the fish data, split it into 60% training data and 40% test data. Now I train it. This is now the support vector machine obtained by training it on this 60% training data. This is the training error. That's how good it gets on the training set. You see we have 5 misclassifications and 73 correct classifications. And now on the test set, you see we have 3 misclassifications and obviously 49 correct classifications, which is roughly a rate of about 5 to 6%, which very much corresponds to the results we had also on the training set. So it seems that in this case, for these parameters, it doesn't really overfit because the training and the test error are almost the same. Okay, if I really overfit strongly, you get something like this. Maybe it's worth looking at it. So this is really overfitting. That means that really the support vector machine tries to memorize every little sample and puts it into the positive class, whereas all the negative samples are more or less the default class around it. So let's look at the training error. The training error is 0. You see, all 78 samples have been correctly classified on the training set, but we have 20 misclassifications and 32 correct classifications. So we have only an accuracy of slightly above 50% compared to 100% accuracy on the training set. Okay. So how can we actually make sure that we choose the right hyperparameters? There's a function tune SVM with which you can optimize the hyperparameters. So there, in the case of support vector machines, there are basically two hyperparameters. Namely, if you have the Gaussian kernel, it's the width of the kernel, and it's this constraint on the coefficients. So they're called, the constraint on the coefficients is called cost, and the width of the Gaussian bell kernel is called gamma here, it's more or less something like the inverse of the sigma. It's 1 over 2 times sigma squared. And this function, in this case, applies tenfold cross-validation to find the best parameters. So to find the parameters that give the best accuracy after tenfold cross-validation. So let's run this. That takes a little bit of time, because actually I have pretty many parameters. You may see here that I use multiple powers of 2 for the cost, for the cost factor, which is the constraint on the coefficient. So I use all powers of 2 from -3 to 5 in steps of 1. So that's altogether 9 different parameters. For gamma, I use powers of 2, powers from -3 to 3. So these are 7. So I have 9 variants of this and 7 of the other. So which is altogether, it means I have to train 63 support vector machines in a tenfold cross-validation setting. So it's 630 support vector machines that are trained. But in the meantime, it has finished, and you see the best performance is an error rate of 5%. That's roughly what we also had with handcrafted ad hoc choices of the parameters. And the best parameters is 0.125 for gamma and a cost factor of 4. But this is basically how you always proceed. You have a training set, you perform cross-validation to actually find the best hyperparameters. The good thing about support vector machines is that you only have few of them. In this case, 2. So you can do grid search. In the case of deep learning, there are so many things that are of interest. So for instance, there is the number of the overall architecture of the network, how many hidden layers and how many neurons in each layer. That's the learning rate. Which activation function, whether to use dropout and at which rate. Regularization things that I haven't even mentioned in my talk. So there are very many parameters. And for instance, even for very simple data sets, I can easily have hundreds of different settings that I have to test. And if you perform cross-validation for deep learning on a large data set, it means that every time you train a network, it takes seconds, maybe even minutes, to train a single network. And then you have this tenfold cross-validation 10 times, and you have hundreds of different parameters. So you have to perform thousands of experiments, all of which take seconds up to minutes. So you can easily end up with computation times for days, even for simple data sets. So you always have to reduce things. And one thing that many people are doing is to not to do cross-validation, although it's generally the better approach, since it multiplies the effort. It's often quite common just to have a fixed split of a training set, validation set, and test set, because that allows you to have train only one network parameter setting. Otherwise, you would have to perform multiple training runs. Okay. Now let's move on to random forest here. I'm loading the data set, and now I'm loading the iris data set. And here you see this is what we get for the iris data set if we apply a random forest model with more or less standard settings and 1,000 trees. And the random forest function, even without any test set or so, gives this out-of-bag estimate that I told you about yesterday. And you see that the overall out-of-bag misclassification rate on the entire data set is 7 out of 150. Okay, there's a little bit of confusion between versicolor and virginica, and if you recall the scatter plot of the data set, these were the green and the blue cloud that were slightly overlapping, whereas the red cloud was always dislocated from the other two, so that's why it's very easy to perfectly separate the setosa class from the others. Okay, here's the variable importance plot, and as I told you yesterday, that's exactly the same plot. A petal length and petal width are almost equally important. Sepal length is far less important, and the lowest, by far lowest relevance is attributed to the sepal width parameter. Okay. Now let's try some sequence classification. Okay. A student of mine has implemented a beautiful package called KEBABs. KEBABs stands for Kernel-Based Analysis of Biological Sequences. And it allows for classifying biological sequences using support vector machines with a sequence kernel. I didn't go much into detail about the sequence kernel, but it's basically a similarity that is based on common subsequences. Okay. So I'm reading a data set, the promoters data set. It's an old data set from the UCI machine learning repository. The UCI machine learning repository is a public repository that has existed for at least 20 years, I think, that collects a lot of benchmark data sets, some of which are pretty old actually, but okay. This is a data set from the early days of computational biology back in the 1990s, if not 1980s. Okay, we can have a check. Let's go to the UCI machine learning repository. Fortunately, it's a little bit slow. Okay, otherwise you have to believe me. I will close this in order not to delay anything here. It's a data set of DNA sequences taken from E. coli. So a bacterial DNA data set. There are two classes, 106 samples, balanced two classes. One class is promoter sequences, and the other is other random sequences. So it's about inferring sequence patterns that hint at promoters. For those who don't know what a promoter is, that's more or less the file header of a gene, nonchalantly speaking in computer science terms. Okay, and this is important to find out where possible genes may start and where regulatory elements may bind. Okay, so we have relatively few samples. This is just pre-processing. This is what the sequences look like. This is what the labels look like. So let's see distribution. It's, as I said, an equal distribution of 53 positive promoter sequences and 53 negative sequences, so random DNA sequences. And the best reported leave one out cross-validation accuracy for this data set on the UCI machine learning repository homepage is, I think, 4 or 5 errors in leave one out cross-validation. By the way, leave one out cross-validation means that you have cross-validation with as many folds as you have samples, which means you always leave out one test sample and train on the remaining. So in this case, we have 106 samples. So we always, we take each of these samples, take it as a single test sample and train on the remaining 105 samples. And then we get 106 results, and we can check how many of them were correct. And as I said, the best reported result was, I think, 5 errors or something. And now let's try how well we can do without any parameter tuning with a support vector machine, a sequence kernel, and kebabs. And actually, the result is an accuracy of 98%, which means we did 2 of the 106 wrong, and we did 104 correctly. So without any great parameter tuning, I outperformed the so-called best result that is reported there. Although I have to admit, of course, that the results reported there are probably clearly not up to date. Okay, so that was a quick tour of basic machine learning, support vector machines, random forests, and even sequence kernels with R. Of course, I don't have the time to introduce every little statement and to introduce R here. But now I want to show you something else. If you want, you can participate in the following. So here I have a data set that I've been using in teaching for quite some time. It's a character classification data set. So I will introduce it to you. Just a moment. I will run this code. Okay. So I read the data set, and now let's visualize what it looks like. It consists of characters in the resolution of 4 by 6 pixels. Okay, so they're 4 pixels wide and 6 pixel tall. Okay, so they're really very crude, very poor resolution. Okay, this does not work in. I will. Use something else. Display it. But here you see that a random sample of 144 of those images. So the blurry stuff, that's the input image, and the numbers shown on top of them is the true class. I think for some of them it's pretty clear that this is a 0, for instance, here, or that this is a 9, but there are also some that are like this 8, for instance, right? Or that this is an 8, or so, and this is a 4. So some of them are really of bad quality. So what do you think? With which error rate can you classify those characters?
Numbers, yeah.
So they're all together in the training set, there are about 3,000 characters, more or less equally spread over 10 classes, 0, 1 to 3, up to 8, 9. Okay. So they're single characters, they're relatively well aligned in these 4 by 6 windows, but they're not perfectly aligned, and they're really handwritten. So there is no reference, more or less. They all look a little bit different. The ones, for instance, some of them are these German-style ones, and some of them are these international-style ones, which is just a vertical bar. Also, if you look at 7, there's some this international-style 7, and there's maybe some German-style 7 somewhere else with a horizontal bar. I don't see one now. Yeah, here is one with an additional bar in the middle. That's how in the German-speaking world 7 is written. Okay, so there is a lot of potential to confuse German-style ones with 7 in the English-speaking world fashion. Okay, so let's try that. Let's start with a really crude approach by simply throwing it into a random forest. So I'm training 10,001 trees, and you see, well, it looks pretty good. Right? This is the confusion matrix. You see here only one time a 1 has been confused with a 7, and only 4 times a 7 has been confused with a 1. The overall error rate, if you look at the out-of-bag estimates for random forest, is 6.7%. So we have 93.3% out-of-bag accuracy. Okay. Now, you get a task. So if you run this code that you load the data set, now you can transfer your code from unit 2, the tune SVM code, and try to run it here. And let's see how far you can get. And in the meantime, I load my pre-made sample here. Okay, don't watch what I'm doing. It takes a while, actually. Okay, I thought we would have time until 10:30. Yeah, okay. Well, I can remove my stuff within 1 minute only. But I don't want to put anybody into stress. Okay. I'm finished with a linear, finished with a linear, tuning a linear support vector machine, and I got a 10% cross-validation error rate, which is not that good, right? Because it was much better for random forest, where I got an error rate of 6.7%. Okay, I don't think I have the time to run so many support vector machines now, because the Google Hangout is taking a lot of performance on my computer. What I can show you is the final results. Okay, so if you go to the zip file with the course material, you will see that every R file, every R code file, is accompanied by a PDF file. And that's a pretty nice thing. There's an R package that runs an R file, that has a function to run an R file, along with creates all the results and displays the results in line with the code, and also nicely formatted. You will find the instructions here in the header of each file. What you have to do, you simply have to install the knitr package, you have to load the knitr package, and you have to run the command stitch. It runs everything and produces a PDF file. Okay, so here for unit 4, for the result, here you see the PDF file. Okay, that's what it looks like. You see all the code, and then you also see here some plot that is produced by the code. Here you see the best parameters for the linear kernel. Here you see the best performance for the linear kernel, the best parameters for the RBF kernel. Interestingly, it's exactly the same parameters as for the fish data set. This is a coincidence. This is not a rule. Okay, you should not believe that 0.125 and 4 are the perfect parameters. Okay, that's really a coincidence. But what you see here is I got an error rate of 5.2% roughly, which I think is actually pretty good for this data set. Okay. Then I train the final model with exactly those parameters. And that's the final confusion matrix on the test data set that I haven't given you. Okay. When I give this task to my students, I always give them the training set and let them optimize the parameters. And then I evaluate the result using the test set that I withheld from them. And I give some extra points to those who have achieved the best accuracies. And you see here the final best accuracy I have with my parameters on a test data set is 94.91%, which I think is pretty good. And now, in order to finally shock you, I show you the result for a neural network. So this is now with the MXNet package that I mentioned just previously. And you see that, well, probably the first large threshold you have to take is to install the MXNet package. It's not an R package that you can install with one command like all other R package from public repositories. You first have to install some libraries on your computer. This is strongly strongly platform, so operating system and a hardware dependent, whether you have an NVIDIA graphic cards or not, whether you have Linux or Windows or Mac. This is all strongly depending on it. So it typically takes a few hours until you successfully avoided all the pitfalls when installing this R package. So you first have to compile the MXNet library, set every configurations right, and then you can build the R package specifically for your platform, which is quite unusual because R packages are usually pre-compiled for Linux, for Mac, and for Windows, and they work on all Windows systems and all Mac systems and all Linux systems. But this is when you build the package specifically for your computer, and then you can install it, and that takes some time. Okay, then you have to select the hardware, which you normally never do. So what I did here in this particular case, that on the server on which I produced this, I chose GPU number 5 because that was the only one that was available at that time when I did it. And there is no functionality for cross-validation. There's just basic functionality for setting up an architecture and for running a training run and for running predictions. But you see, if I want to try different parameters, I have to write code for cross-validation and for setting up the network myself. This is what you see here. So it's a lot of code. You see here that's all the parameters that I took. So I have no hidden layer, one hidden layer with 50 neurons, one hidden layer with 100, 1200, 300, two hidden layers with 25, 25, 50, 50, 100, 100. So only the architecture corresponds to 1, 2, 3, 4, 5, 6, 7, 8 different parameters. And this is by far not an exhaustive search. This is just an educated guess. Then the number of iterations to do the training, the learning rate, I have 3 different learning rates. I have 4 different momentum coefficients. This is something that I haven't even mentioned. I have 3 different dropout rates. So altogether, this corresponds to 792 different settings for a neural network in a double 5-fold cross-validation setting. So I only randomly choose 5 of the 792, okay, to finish this within finite time, so to speak. That all took together about 4 minutes, okay. If I ran all the 792, then you can imagine that this would be approximately 100 times as much, more than 120 times as much, which corresponds to between 2 and 3 days. Okay. Well, maybe less, but I once did it, and it took 2 to 3 days because I was not running the only job on the GPU, and if the GPU has to be shared between multiple jobs, then the slowdown is dramatic. Okay, so if you're lucky, You can do it in 500 minutes, which is more or less, I don't know, 8 to 10 hours. If you're unlucky, if you have slow hardware, or if you have to share the hardware with somebody else, it can take up to days for something for what a random forest takes seconds. Or a support vector machine, cross-validation, hyperparameter optimization takes maybe a few minutes, okay? But the good news is, in the end, the result is pretty good. So even with the five randomly chosen parameter settings, I get an accuracy on the test set of 94.66%, which is almost as good as I think we had 94.91 or 94.92 on the for support vector machine, and we are almost as good as the support vector machine, and we could be slightly better, though not dramatically better than with the support vector machine, if I tried all the 792. Okay, but this is basically what the code would look like. This is just one random solution based on MXNet with the R package. I chose this solution just for consistency, that everything works on the basis of R. I would normally do it rather with the Keras layer on top of TensorFlow. That's also something that I think a beginner can handle quite well, and where the amount of code you have to write is about of that size, okay? But it's based on Python, and it also requires a lot of computation time and so on. So, but I think in the course material you also have this solution. So if you want to go deeper into it, please feel free to try it. You will first have to install the MXNet package, which is a special challenge, I think. But okay, if you want to try, please feel free to do so. And if you have any problems or troubles, or if you have any other questions regarding to machine learning, I will be happy to answer it. And since I'm already a little bit over my time,
We have one question from a colleague that is following the presentation via streaming.
yes,
So,
okay.
so if you can.
This is a question from Nacho. I don't know whether this is a nickname or
Ignacio is the name.
Ignacio. Okay, so Nacho is a nickname. Yeah. Okay. So hello, Nacho. The question is that if machine learning is about classifying new data from old samples, this assumes that the data is invariant over time. And yes, I can confirm that this is really true. Okay. I said yesterday, if you take training samples and test samples from one common data set, and you randomly sample training and test samples, the assumption is that they all stem from the same distribution. And under this assumption, it is true that the test error is an unbiased estimate of the performance on future data. But however, if things change over time, if the distribution is not time invariant, this is no longer true. So it's absolutely right. If you have time dependency, and then this does not hold true, okay? What you can do in some ways is to do training and test separation over time, or cross-validation, where you leave out a window of time to check how well the model that you create on this time period generalizes to another time period. But that also assumes that the way things change over time remains constant, okay? So that's a sort of next level invariance. If things change chaotically, unpredictably over time, then you cannot predict anything. But that's, I think, also very clear that this is impossible then. If I have no idea if things really change randomly without any systematics, then I will not be able to make any predictions about the future, and then machine learning is not the right approach. Then probably the going to the casino or throwing a dice is the right approach. Is the right approach. Okay. So okay, sorry, I cannot unlock the iPad anymore. Okay.
I think that's it.
Okay, sorry. Yeah.
Okay.
Okay, does that answer your question? Okay. Thank you for your question. So, any other questions? Yes?
Would you recommend to use the data set randomly to train the machine learning? To use to select a part of the data set randomly, besides or selection by any particular reason, like differences between parameters or any kind of reason.
Okay. I'm not sure if I got the question. So,
how did you recommend to select the data set?
okay, I would not recommend a particular data set. You can never make a claim about the general optimality of a certain method. I would not start from a method, or I would not start from a. I would rather say, if you have a data set, an associated question with it, then you have to select the method. Okay. So you can never make a claim that generally a neural network with these parameters is best, or a random forest with those parameters is best. So you always have to start from a data set. If you run multiple machine learning algorithms on every UCI machine learning repository data set, you will find out that for some neural networks will be best, for some random forest will be best, maybe for some support vector machines will be best. And I don't have a problem with that, actually, because it's clear that there is nothing like as a free lunch. That's a famous saying. There is nothing for free. Basically, it means that there is no perfect answer to every question, which means if you have a data set and you want to get the best out of the data set, then you really have to focus on this data set. You have to try out every method, well, unless you can exclude some for basic technical reasons, because it's generally known to be a bad method, or if it's not applicable because it doesn't fit to the structure of data or something like that. But for instance, support vector machines, random forests, and neural networks are all three are very, very common. They're accepted. They're known to be good, and they're known to work for a wide variety of data sets. So I would, if I really want to have the best for a concrete data set and a concrete question associated to it, I would try all different variants. I would try all possible or many possible different parameters to get the best out of the data.
Thank you.
You're welcome. Any other questions? Okay, I think in the interest of sorry.
So with the neural network, the result of the accuracy score is not so different. Like
not in this case, but I think
because it's a small data set.
Yes, it's a relatively small data set. It's the maximum accuracy you can have is strongly limited by the quality of data. We have seen the characters, right? So if you have high resolution images of characters, I'm very, very sure that a convolutional neural network will do much better. So this is not a very accepted benchmark data set. It's one that I did myself, right? And because of the resolution, it makes more sense to use a fully connected network, so with 24 inputs. But if the most common character recognition data set is the so-called MNIST data set. It's also a digit recognition data set, but it has 784 pixels. And I think for this data set, you very, very easily outperform other methods with a convolutional neural network. And I think the rates that you get are above 99% and not only 94 or 95. Okay, so this is probably not the most typical data set. This is not the data set where neural networks can use their full potential. Okay, I think in the interest of time, we have to finish now. I think we have to be out here in 2 minutes. So thank you.
If you have more questions, you
Yes, we can talk offline outside. Okay. I thank you very much for your attention so far. I also very much thank the people who watched my presentation online. So thank you and goodbye. I hereby close this session.
Thank you.